Okay, well, thank you very much for inviting me to this exciting seminar. You know, one good thing about this, COVID, I mean, there is nothing really good about it, but, before that, I didn't really know about using Zoom, but now, it's really my tool, to connect to the world. So it's really exciting that to be able to talk to you, someone in Europe and someone is in the United States, and at in different time zone. So today I am going to present my research on children's inference in learning word meanings. Inductive, analogical, and abductive inference. So children need inference in order to learn the meaning of words. As verbs refer to relations between arguments, verb learning requires relational analogical inference, something which is challenging to young children. In this talk, I will explore how young children overcome this challenge. I discuss how children use a chain of inferences to learn meanings of verbs. I consider not only the process of analogical mapping and progressive alignment, but also how children use abductive inference to find the source of analogy and gain insights into the general principles underlying verb learning. So verbs refer to kinds of relations. And since learning requires relational analogy, I do not think I need to introduce Professor Deidre Gentner's seminal work on the relation between analogical reasoning and verb learning to people here. To learn meanings of verbs, children need to decompose the scene first into lower order elements that are mostly objects in the scene, and then align them and extract higher order element, which is the relation between the objects. Children then need to map only the relation part to the verb, suppressing attention to the object. But this is quite difficult for children younger than 4-year-olds. So please see this very simple experiment. So in this cross-mapping experiment, children were taught a new verb to the standard object. They were then shown 2 test videos. So here I say, look, the rabbit is fepping. And then children were shown 2 test videos. Okay, so, and then ask, which one, where is fepping? Okay, and as you see, the correct answer in light of, in eyes of adults, the correct answer is, of course, the bear doing the same action. But even in this simple cross-mapping task, 3-year-olds, both Japanese and English learning ones, failed to generalize the newly taught verb to the same action event. In this different experiment, this video includes both an actor and it's a transitive action scene, including an actor and the patient object. Okay, and then again, we say, look, she's fepping it. Okay, and then children were presented with 2 test stimuli, one with the same action with a different object, and this one, the same object with a but action is changed. Here. Okay, and here, as you see, even though the three odds, well, the graph shows that the y-axis shows the proportion of the same action response, okay? The same action response. So for nouns, the correct answer is the same object one, right? So their choice should be raw. And then their choice was raw, right? So they had no problems. 3-year-olds had no problems with the noun condition, but 3-year-olds could not generalize a novel verb to a new thing with a new object, you know, to the same action with a new object. So, but 5-year-olds were successful in doing it. The difficulty of verb learning has been found across different languages. So I replicated this study with 3 language groups, again, Japanese and English and Chinese. And in all 3 language groups, 3-year-olds could not generalize newly taught verbs to the same action scene. However, children, there are ways to bootstrap children. Children can overcome their difficulty by some bootstrapping mechanism. And one big driver of bootstrapping mechanism is progressive alignment. Well, this theory is was proposed by Dietrich Gentner, and so this theory says that lower when mapping relational similarity, children align the entire thing from lower order elements to higher order elements, and lower order concrete similarity helps young children to find higher order relational similarity by highlighting the overall similarity to the entities. So example would be, so when children were given an opportunity to simply compare the initial model, the hiding room 1, with another highly similar model, they became better able to find the toy in the target room subsequently. So overall similarity or perceptual similarity helps children to go from perceptual similarity to higher order relational similarity. Okay, so what about verb learning? Is there a way to help children to make inferences about verb meanings, relation-based verb meanings? So the answer is yes. My colleagues and Haru and Okada and I increased the object similarity. So as you see, the control condition is the object dissimilar condition, which was the same as our original Imai et al. 2005 study, right? So so here, you know, children learned a new verb, ducks, you know, she's ducksing it. And then, you know, they were shown two test events, and the correct event, right? Action same event was the same. I'm sorry, the perceptually dissimilar object was used. So this is a dissimilar condition, object to dissimilar condition. However, we also set up an object similar condition where, you know, the object is just in the same action scene. The object was displaced but this displaced object was perceptually similar to the original. Here, when we compare the two conditions, look at the 3-year-olds' performance. They were still around chance. They did not grade, but compared to the object dissimilar condition, they did much better. And 4-year-olds, they were below chance. Well, not at chance, I'm sorry. 4-year-olds were at chance with the dissimilar object, but with the similar object, their performance went up to 80%, right? So object similarity does matter, make a difference as progressive alignment theory predicted. Okay, and so another question, further question that we addressed was whether the experience of successful relational verb learning with perceptual similar object transfer to cases in which lower order similarity, that is perceptually dissimilar object, lower order similarity is wrong, so that is the perceptual dissimilar object. So what we did was, as the entire experiment, we set up 8 trials altogether. But in the similar dissimilar condition, the children saw, during the first 4 trials, they saw trials with similar object sets. And then they move on to the last 4 trials, in which the replaced objects were dissimilar to the original scene. Okay. In another condition, which is the dissimilar condition, the dissimilar object was used throughout the experiment. Note that the set, the stimuli were the same for the last trials, right? So for both conditions, children saw dissimilar objects for the action same thing. Here is the result. Okay, so again, this is experiment 2, and the first 4 trials, again, oh, by the way, the participants' age was 4-year-olds, because we wanted to see, based on the result of experiment 1, we thought that the 4-year-olds, at 4-year-olds, we may see the maximum effect of bootstrapping. So, we showed 4-year-olds, Japanese children. Here, the first 4 trials, replicating the result of study 1, the similar dissimilar condition, children were able to generalize the verb based on relations, whereas children who were in the dissimilar condition failed to go beyond chance. Okay, and now at the last 4 trials, where the even similar dissimilar condition, children saw dissimilar objects, but here so children in the similar who experienced the action same scene with similar object, we didn't give them any feedback, but just they chose the similar the action same choice in the similar dissimilar condition, and that transfer to the cases when they saw dissimilar object for the action same thing. So so we now know that just seeing 4 trials with similar object, perceptually similar object, that effect transfer to duration-based verb generalization, even when the object is dissimilar. So it's a very powerful, progressive alignment is very powerful tool to bootstrap children. Now, the new question is, can we get 2 or 3-year-olds generalized verb based on the duration? So what we didn't do in the Imai et al. 2011 study was we didn't provide multiple examples. So we just show one training example and then, tested them. But the literature suggests that comparison of multiple examples also promote progressive alignment. So, so we know that verb learning would benefit from the comparison of multiple events, and providing multiple events and contrasting against the non-different actions sometimes get even 2-year-olds generalized verbs based on relations, right? So in the new study with Jane Childers, we try to combine, we try to give a maximum scaffolding to 2- and 3-year-olds by combining multiple examples and object similarity. So we have 2 conditions. So similar object first condition and all object buried condition. So all object buried condition, children saw perceptually dissimilar objects for the same action throughout. Okay, but first in the similar object first condition, children saw perceptually similar object first. Okay, and then for each action, they saw 3 different trials, 3 different scenes with 3 different objects, and then we did 2 test trials. Okay, in one test trial, the same object was, this is the test video 1 was a cross mapping test. So the same object as the training was used, but with a different action. And then test video 2, we contrasted the learned action and then new action, but the objects were both new. Okay, so we wanted to know if that makes a difference, but also our most interest was to see whether this multiple examples and similar first, seeing the experience the verb with 3 different objects, with 3 different perceptually similar objects, scaffolded 2- and 3-year-olds to relational verb generalization. Okay, so here's the result. So yeah, we did get 3-year-olds go beyond chance. So 3-year-olds were able to generalize a novel verb based on the relation or based on the same action when the multiple example was provided with perceptually seeing perceptually similar object first. However, we couldn't get 2-year-olds do that with Japanese children. I understand that Jane Childers are now testing English speaking children, and then they were showing that they are going above chance, like the 2-year-olds are going above chance. So it may be that English children are able to, 2-year-olds are able to generalize novel verbs based on relations with this maximum scaffolding. So, so in any case, so with just one trial with perceptually dissimilar object, 3-year-olds, 3 and 4-year-olds have difficulty to show verb relation-based verb generalization. But with redundant multiple cues, younger children can learn relational meanings of verbs. Okay, so you know, if you provide more and more redundant cues, younger children can succeed. So right, so sometimes, you know, you can get 2-year-olds show relation-based verb generalization. And so that suggests that you can't say that verb generalization or verb learning is difficult under 3 or under 4, right? So it's a matter of how much scaffolding you provide, right? So if young children have sufficient scaffolding from multiple redundant cues, they can do that by progressive alignment. But also, it's not only object similarity that bootstrap young children. Young children sometimes can use similarity other than object similarity. So in this study, we used sound symbolism. Sound symbolism is a cross-modal iconicity or similarity between word sound and indifferent. So this is the same video that I showed before. So here, you know, when we say, look, the rabbit is fepping, English and both English and Japanese children couldn't generalize the verb to this scene when which the object was, the actor was replaced. However, when I say, look, the rabbit is doing battle, you know, battle, it's a nonsense, you know, coined sound symbolic words that we created, you know, based on Japanese memetics. And here, so when we say non-sound symbolic verb like fepping, you know, their performance, that was a chance, didn't go above chance. However, when we used sound symbolic verb, both not only Japanese speaking children, but also English speaking children who never heard Japanese memetics were able to generate the verb above chance, highly above chance. And then there was like 30% gain here, right? So what I wanted to say is young children are extremely versatile and good at recruiting useful cues to come up to the most plausible meaning of the word in a given situation. And then there are many cues that children can use for verb learning. And of course, you know, there is syntax, you know, so syntactic cues are very important for verb learning. And then children are able to recruit and then use them to constrain the meaning of the verb. And we show that sound action iconicity also scaffold children. Object similarity is helpful. And also, you know, cross-situational statistics could help children learn verbs. Okay, and also language-specific lexicalization patterns, knowledge, you know, so by 2, you know, by 3, children have learned language-specific lexicalization patterns, and then sometimes, you know, they can use the knowledge of this pattern for novel verb learning. Okay, so there are lineups, right? So a number of different cues. But if you have so many cues, then the big question is, how do you find useful set of cues in the situation to begin with? And how do they weigh these different cues? So not all cues are available at the time children make inference about the meaning of a given word. So sometimes different cues and sometimes different cues suggest different interpretations. So children have to choose which cues they trust or they use, and then which cue they ignore. And then also, the same cue is weighed differently across languages. So let me, so this is the verb learning experiment that I showed you. Sorry about the sound. We really need the video. So this is, I told you that we conducted this experiment with 3 languages, English and then Japanese and then Chinese, and each language have different linguistic properties, okay? So in English, verbs are usually said in the full argument structure with no noun omission. In Japanese, argument dropping is more natural when the arguments can be easily inferred in the context. So in English, you know, so when I showed the original scene, you know, I first had a condition. We had a condition in which we said, look, dachshund, look, dachshund. And then children, even 5-year-olds, couldn't generate the verb. But when we say, look, she's dachshund it, you know, so it just, you know, they needed she and it, which, you know, semantically children could see in the video. But English-speaking children needed that information. However, when we did the same with Japanese children didn't do so well with the full argument sentence. And then they did better when we just say, look, dachshund or neketeiru with arguments, 2 arguments dropped, right? And then Chinese is a very interesting language. In Chinese, morphological cues, you know, so they don't morphologically distinguish nouns and verbs. So morphological cues are lacking. So unless the full argument is provided in the sentence, the listener cannot tell whether the word is a noun or a verb, right? So when we show the video and then say, look, a Chinese word only, you know, even adults couldn't tell whether the word is a verb or noun. Okay, and I couldn't tell you the details of the experiment, but what was interesting was that so the linguistic cues are quite used quite differently across 3 languages. So Japanese 5-year-olds, so to begin with, 3-year-olds in all languages couldn't do it. Okay, so it was only 5-year-olds, and then in 5-year-olds could go above, you know, they went above, they could generate a verb above chance, but only in a particular condition. So in Japanese 5-year-olds performed the best, and then they went above chance when the verb was said without the argument. English 5-year-olds performed best when the verb was said with the full argument structure. And what was striking was Chinese 5-year-olds. what Chinese 5-year-old showed an extremely strong object bias, even when the verb was said with a full argument structure. And we tried different linguistic structures, really highlighted verbness, right? So to make sure that children could tell that the novel word was a verb, not the noun, okay? But they couldn't, these linguistic cue didn't help them. And then what helped them was a contextual social cues. So Chinese 5-year-olds paid very strong attention to contextual social cues, and with them, they were able to generate a verb about chance. We provided the same social cue to Japanese and then English 5-year-olds, and then their performance didn't change at all. So, so children are kind of adaptive to their ambient language and use cues that are most helpful and then efficient for word learning. And this result suggests that children also use statistical cues, right? And then they combine statistical cues and analogical inference to come up to the best possible interpretation and then strategy to learn new verbs or new words. So this pattern is like abductive inference. So children come up to the most plausible meaning of a new word by integrating and then coordinating different sources of knowledge and then information in the situation in response to perceptual situational cues that they observe at the moment. And then this inference is like what scientists make to form most plausible hypotheses given available data and then evidence. Well, this was originally pointed out by Charles Peirce, and then elaborated by Sogard. So, so here, analogical inference plays a key role for inference of word meanings. But how do children find the source of the analogy? To come up with the hypothesis, usually, scientists use analogy. But now the first thing they have to do is they have to know the source domain. And then that requires kind of intuition, right? So the same, the same is true for children. Drawing analogical inference to learn verbs. So finding the source of analogy requires abductive insights, as is the case for scientists forming hypotheses. And, some people propose that children are good at detecting statistical distributions and make Bayesian inferences to go beyond the observation. But to make Bayesian inferences, you have to find prior, and then finding prior also requires abduction. And shifting from meanings based on perceptual similarity to those based on relational similarity also requires abductive insight. Right? So gaining insight requires abductive inference. So now, let us stop and then think why non-human primates do not learn language in the real sense, even though they are pretty good at statistical and then associative learning. So in my view, learning by, this is because they couldn't draw analogy in a relational analogy. They could draw some analogy, but in a true sense, they are weak at making analogical inference, relational analogical inference. At least it's very limited in animals. And that, and that is because they cannot find source of source for analogy, which requires abduction. So, so this is the hypothesis that I've been entertaining. So importantly, language is founded on the symmetrical relationship between symbols and referents, and understanding this bidirectional relationship is critical for word learning. So suppose that a mother picked up an apple and then said to the boy, look, this is an apple. It's called apple. If the child seems to remember the sound apple and is able to say the word at that time, the mother naturally expects that at a different time, the child will be able to pick up the red round object called apple when she or he asks, when the mother asks the boy to get her an apple from a bowl which contains various kinds of fruit. When the boy boy was able to choose the apple among different kinds of fruit and hand it to her, the mother would not think that her boy made an inference, great inference, a kind of inference that most non-human animals cannot make in order to respond to her request. But please see this video. I'm sorry, unfortunately, it's the sound is in Japanese, but I will talk over the video in English. So this is Professor Tetsuo Matsuzawa, a famous primate researcher, and he had trained this chimpanzee eye, the association between a symbol and color. But the way he did was he showed the color, and she was to choose the symbol that matches the color. And she remembered very well, even though the training was completed 2 years ago. But now he started with the symbol and then asked her to choose the color. So the contingency was reversed. She couldn't choose the right one. Well, right in the sense of human, but she was never trained the association from the symbol to color. So did you understand the video, what the video means? So, so this video, I hope that you were persuaded by the video that making bidirectional connections or bidirectional understanding bidirectional relations between symbols and the different is something that humans do, at least human young children do, children who are actively learning word meanings do all the time. And then otherwise they couldn't learn words, right? But, decades of, so animal researchers or researchers of comparative psychology failed and then failed in demonstrating that non-human animals, various species could do the symmetry inference. So they failed in chimpanzees, they failed in rats, pigeons, baboons, many different species. So decades were spent just to show that non-human animals wouldn't. So we don't know that they couldn't or wouldn't do symmetrical inference, right? And this unwillingness was so robust that some researchers even trained chimpanzees in 2 directions previously, and then, tested with a new set. So even chimpanzees who were language trained and received both direction training couldn't show the evidence, or couldn't use the symmetry inference when the contingency was switched. The direction of contingency was switched. So, in the new, relatively recent paper that we published in Cognition in last year, I think it's 2021, we wanted to know that when human infants started to make the symmetry inferences, one possibility is that, this ability or disposition to make symmetry inference or bidirectional inference is available, probably innate and available prior to language learning or semantic learning. But another possibility is that this bias arises as a consequence of word learning. And then that, knowing this, would give us some interesting insights about the origin of language and origin of uniquely human way of thinking. So what we did was, first we tested human 8-month-olds and then adult chimpanzees. So this is a comparative study. And we trained two contingency. And we used a looking paradigm. We didn't do operant conditioning because we couldn't really do, operant conditioning with human infants. So we tested 8-month-old who were said to be, who are before, who still haven't started active semantic learning. So if we found evidence for symmetry bias in infants at this age, we are probably, we may be able to conclude that this bias is available before language, and then it could be innate or innately available. But another thing we wanted to know is that whether chimpanzees might show the symmetry inference with this new paradigm, the looking paradigm, because in the previous studies that researchers really failed to show, repeatedly failed to show symmetry bias, they always used the operant conditioning where, so they choose, they respond, and then they received a food reward, right? But when the contingency started, the trial didn't start with food, like food reward, right? So they may, that the animals may have thought that the food reward was also included in the contingency, right? So in that case, without starting with food, they have no reason to show the symmetry or symmetry bias. So we started, we wanted to try this looking paradigm with eye trackers, with chimpanzees as well. And what we did was we showed two set of contingency. So in one, we counterbalanced everything. But in this example, we had two objects, so dog and dragon. And then dog was, so we showed dog for a while and then disappeared. And then a ball appeared, and then zigzag movement followed. And when the dragon appeared, so appeared on the screen and then disappeared. And then it changed into a ball, and then a curvy movement was shown, right? So we trained the contingency, but train means that we just saw, familiarized the two contingency pairs to children and in chimpanzees. And then when they were habituated, we switched the contingency, started with the motion or movement, right? And then the question was, if infants, human infants, and then chimpanzee expected to see the paired object at the symmetry test, or they were surprised when the pairing was broken. Okay, so here the result. So as we kind of expected, only human infants detected the violation, showing, meaning that human infants at 8 months, before they started active semantic learning, have this symmetry bias. And then they expected, or they assumed that the association hold even when the contingency started from the reversed direction, But, the chimpanzees replicating with the previous result, tons of studies, they did not care, right? So their looking was exactly the same between the symmetry condition and so symmetry means that pairs were retained, and violation condition in which the pairing was broken. We, of course, with the null result, with the experimental condition, we have to make sure that chimpanzee learned the contingency in the order, the original order, from the object to motion order. So we conducted a control experiment, and then in the same order, we at test we showed the same event and the switched event, and then in this case, chimpanzee discriminated. So they showed the preference for the consistent pairings rather than violated. So the preference, direction of preference was different for chimpanzees and human infants, but so in all chimpanzees showed this discrimination. We had 7 chimpanzees participated. Okay, but at symmetry bias test, at an individual level, their performance varied, right? So some showed longer looking at the violated, or some showed longer looking at the consistent, right? So it seems like chimpanzee do not show the symmetry bias in this task too. So we wanted to know whether human infants have even younger children, infants show the symmetry bias. And then also we wanted to try, we wanted to know whether this symmetry bias can be seen on a more standard matching to sample paradigm, which is really standard for testing symmetry bias for chimpanzees or non-human animals. So, so I just tell the result. I mean, if you are interested, I can show the result, the graphs during the Q&A session. But what we found was human infants make symmetry bias even at 5 And then here we didn't test animals because this paradigm was exactly what other researchers used, right? So just to summarize the result, what we know was human infants make symmetry inferences, which is a type of non-logical heuristic reasoning, but chimpanzees do not. And symmetry inference, so the symmetry inference is human-specific cognitive function, and it may be a critical prerequisite of language learning, and another uniquely human flexible heuristic thinking. And probably, you may wonder why this is so critical. I mean, of course, watching the video of the chimpanzee, failing to assume that the matching between symbol and color, you may agree that it's important, but why is it so important? It's important. The symmetry inference is important for language learning in even a different sense, and a more important sense. This symmetry inference is intensely studied in the framework of stimulus equivalence by researchers of animal cognition, because it is an advanced form of abductive inference, which enables learners to learn relations that have not been directly trained. Here, so let's think about the three-way relation between among a referent, an apple, the sound, and the letters, the sequence, letter sequence apple, okay? So stimulus equivalence, I think this term was named by a comparative psychologist, Sidman. And stimulus equivalence refers to a special condition whereby derived relations are spontaneously learned without direct experience by means of two operations of inference, namely symmetry and transitivity. Suppose two contingency relations, if A, then B, and if B, then C, are taught to a child, as this figure shows. And then by making the transitivity inference, the child spontaneously forms a new relation, if A, then C. Now, we know that by the many previous studies on animals, we know that animals can make transitivity inference, right? But if the transitivity inference is combined with symmetry inference, if the symmetry inference is available, the child can additionally learn three other relations, B then A, and C then B, and then C then A. In short, children end up learning 6 relations by being taught just 2 relations. So this mechanism offers a way of rapid expansion of knowledge and making abductive leaps necessary for language learning. So I might be, if I may allow, I might be bold to say, the prerequisite for language acquisition could be among others. I wouldn't claim that these are these 3 prerequisites, but these 3 could be add to the previous insight or previous proposal. So one is actually, it's not new at all. So one ability is ability to detect similarity and then form categories based on perceptual or conceptual similarity. And second is ability to recruit useful cues, combine them, and then weigh them to produce a most plausible hypothesis. And to do that, probably, this inference is supported or combined by statistical learning. The third prerequisite is ability to bootstrap from perceptual to relational similarity by making abductive inferences. So the last word is human children have incredibly powerful ability to learn by drawing a chain of inductive. Statistical learning is a type of inductive inference. So inductical, analogical, and abductive inferences. And then there, analogy plays a key role. In fact, some people may think that analogy is abduction, right? But I think abduction is broader than analogy. So analogy is a special type of abduction, I would say. So in any case, analogy really plays a very important role for language learning and conceptual development. Much has been studied to reveal the developmental trajectory of analogical reasoning, and then how we can scaffold children for relational analogy. But if I may propose, more research is needed to uncover how children can find a source domain for analogical inference and how children can make abductive inferences. Okay, so that's it. Thanks for listening.